In this video, I want to talk about pipeline design. Why? Because in Alberta in Canada, we have access to a lot of gas that we need to distribute across the different cities. To do that, we need to design a network of connection between the cities and figure out what amount of flow are going to go through every pipeline. So to simulate a potential solution to that, I built this application. It downloads data from simple maps to get the position of cities. We compute the distances between them, and then we compute the minimum spawning tree. We optimize the flows across these pipelines, and then we displays on the metric on the Plotly map. So to go over the application itself, it's available at pipelinedesign.fly.dev. In this application, you can choose to the number of cities, how much capacity there is on every source of city, and the average demand per sink. So here on the very simple example, I can just rerun it, but you can see that we have Edmonton here with a certain amount of inbound, outbound. So since this is a source node, it only distributes around the neighborhoods. Then we can see that similarly here at Calgary, we also have a source node that serve neighborhoods. Now here you can see that we don't have enough demand to satisfy all the neighborhood, so we can increase it, for example, to 200 for the capacity, and at that point we don't have any unmet demand, but we have some unused capacity. So you can play around with the number of cities. So here, if I increase the number of cities, it will re-optimize the network for the new cities and re-optimize also the flow accordingly. So you can see that if we increase the number of cities, we once again don't have enough capacity to serve all of the demand. I'll go over the code a little bit to give you an idea how I built it. So in source, we have the first thing to note that is important is the mst.py. In this file, this is where we optimize the network itself, and we use Kruskal algorithm. This is quite a bit more efficient than trying to solve it using a general purpose solver, mostly because the number of constraints scales exponentially with the number of cities. So after 20 to 30 cities, the problems becomes infeasible for general purpose solver. So you have to use an heuristic for it, but it works quite well for this purpose. You could use this algorithm as an initial feasible solution and then optimize it with local search. So once you have the design, you need to optimize the flows. I experimented with two different ways, either with Gurobi or Highs. Gurobi, I experimented with it first, but you need a license, so I couldn't deploy it. So that's why I built also a version with Highs. But today with LLMs, you can just pass in, for example, the documentation of Highs, and then tell the LLM, can you translate from Gurobi to Highs, and it works first try. So here you can look at the code itself. It's very straightforward. We have flow variables, we have unmet demand and unused capacity, and here we have the objective function where we want to minimize flows and also unmet demand. We have flow conservation on both source nodes and sink nodes. And then that's it. We also forced to use all available capacity or satisfy all the demand depending on where we are bound by. And then we just save the solution to the model. Note that for the data, we use simple maps. So we just download the data directly. It's open source. But you still need the license, but you just need to tell them that you're using their data. And finally, we have the UI itself where we display all the information about the flows in the Plotly map. Note that here, for example, I experimented with both Gurobi and Highs, but I removed Gurobi because of licensing issue. So that's the demo. I hope you enjoyed it. Thank you for watching. Bye-bye.